Hi again, and welcome to this video where we return to studying learning theory, this time generalizing the results that we saw earlier to infinite hypothesis sets. So just as a last recap, the last time we looked at learning theory, we basically introduced learning theory as an approach for giving mathematical guarantees on the closeness of the in-sample error and the out-of-sample error of a hypothesis learned by a learning algorithm. Right, so there were basically two things that came into play, and the most interesting thing here, or the one that we care about, is really the out-of-sample error, what we denote E out. And the basic setup was, again, that the way the data is generated is that we have some input domain X, maybe it's d-dimensional feature vectors, it could also be another input domain, and we have an output domain Y, which is the labels that we're trying to learn. And we assume that there was this unknown distribution D over the input domain, giving us, say, feature vectors. And there was this unknown target function, at least in the simple case, with the deterministic target function mapping input elements from the input domain to labels. Right. Then we also focused on the 0-1 loss for binary classification, where to find the out-of-sample error is now the probability over drawing a new point X from this unknown distribution, the probability that the hypothesis H misclassifies the point, meaning that it returns a label different from what the unknown target function would assign. Right. Similarly, the in-sample error E that we denoted, it's the same setup. The data still comes from the same unknown distribution D, still this unknown target function F, and the input now are the n training examples given to the learning algorithm, right? So these are n pairs, xi comma f of xi, giving us feature vectors and the corresponding label. Okay. The in-sample error, then again, for the 0-1 loss was just the fraction of mistakes that we make on the training data, right? We average over all the points and count one whenever we misclassify a training example. Okay. So basically, we wanted to relate these two quantities such that if we minimize the in-sample error, we're also minimizing the out-of-sample error, which is the one we really care about. Right? That's the whole idea. So what we proved was using the Höfting inequality together with the union bound, we proved that if I have an algorithm that produces a hypothesis H star, then the probability here over the choice of data set, right? So this is the training example set, the set of n examples, that's the random part. The probability now that the in-sample error and the out-of-sample error of this hypothesis that we learn are further apart than any precision epsilon that we can choose is no more than 2 times m times e to the minus 2 epsilon squared n, where m is the cardinality of the hypothesis set, right? So this is a number of different hypotheses that we search through. And n is the number of training examples, right? And H star is the hypothesis learned by the learning algorithm. Okay. So what we also saw was that this inequality here, this formula, really doesn't work if we have an infinite number of hypotheses. Like, for instance, which is the case for many of these learning algorithms that we've seen, for instance, just using a line in 2D or a hyperplane in general to do classifications based on the side of the hyperplane. There are infinitely many hyperplanes, as you can see here, where we can put infinitely many different hyperplanes that are all sandwiched between the red points and the blue points. Right. So if you plug in infinity in this bound, it doesn't give us anything meaningful. Right. So this is what we'll try to study today. How can we actually deal with such infinite families of hypotheses? It will be the focus of both this video and the next one. Okay. So what hopes do we have, right? Do we have a chance of proving something similar for infinite hypothesis sets? And to answer that, I guess we really need to understand, where does this m in the generalization bound up here, where does it come from? And if you remember how the proof went, the proof of this statement up here, what we said was that, well, the probability that the in-sample error and out-of-sample error of the hypothesis learned by the algorithm being more than epsilon apart is no more than the probability that there's at least one hypothesis in the hypothesis set whose in-sample and out-of-sample error are more than epsilon apart, right? Simply because the learning algorithm has to return one of those m hypotheses. The one that the algorithm returns can only have a far apart in-sample error and out-of-sample error if there's at least one in the hypothesis set with a far apart in-sample error and out-of-sample error. So that's where the aim came from, because we upper bounded the probability of this OR, like this, the probability that the first hypothesis has a far apart in-sample and out-of-sample error, or the second one has a far apart in-sample error and out-of-sample error. We bounded the probability of this by just upper bounding it by the sum of the individual probabilities that the first hypothesis have a far apart in-same layer and outer-same layer, the second hypothesis have a far apart in-same layer and outer-same layer, and so on. So we upper bound it by the sum. And the way we proved it was basically a proof by picture that the probability of a union of events, meaning the probability that we're inside at least one of those clouds, is no more than the sum of the probabilities, because when we're summing up the areas of these clouds, we're just overcounting some of the regions, right? We're overcounting some mass. So that's basically how the proof went. And of course, like this, if we have an infinite number of these events that we're summing up, then we're going to lose. So the thing is that in this union bound, the basic observation that we will try to use is that this union bound is really wasteful if the hypotheses in our hypothesis set are very similar. Okay, so what do we mean by that, right? So let's try to give it like a sketch by a proof by picture again, why this is the case. So for instance, right, if we think of each of these events, E1, E2, and E3 as the probability, let's say that the first hypothesis and the hypothesis set have a far apart in-sample error and outer-sample error. E2 is maybe the probability that the second hypothesis, or is the event that the second hypothesis have a far apart in-sample error and outer-sample error. Maybe E3 is the event that the third hypothesis have a far apart in-sample error and outer-sample error. And then, you know, maybe it could look like this, that basically whenever one of them happens, they all happen. Which would basically mean, right, that if you think about it, if you have all these hyperplanes here that are very, very close to each other, even though they are different, then in some sense, right, if one of those have a very far apart in-sample error and outer-sample error, then intuitively all the surrounding ones also have a far apart in-sample error and outer-sample error, which means that these events, right, that one of them has a far apart in-sample error and outer-sample error, they're really very overlapping. So when we're just saying that we're just summing up the areas of the probabilities of all these events, we're really overcounting a lot. Right? And that's where the union bound is wasteful. And this is where we'll try to do something better. Okay, so what we'll try to do is that we want to find a way of exploiting similarity between different hypotheses. And of course, the intuition is still, if what we said last time is true, then somehow a more complicated hypothesis set should somehow give a worse generalization. Maybe at least that's the intuition that we got from last time. And we'll try to see that this is still the case. And in some sense, right, even though there are infinitely many hyperplanes, lines like this, there's also infinitely many of these curves and so on, right? But over here on the right-hand side, somehow this is a more complicated hypothesis set than the first one, even though you know, they're both have infinitely many hypotheses. Okay, so we'll try to come up with some definition or something that can capture the difference between these three types of hypotheses. Okay, so somehow we want to find a measure of complexity that's not the size of the hypothesis set, because that doesn't really work for infinite hypothesis sets. Good. So what we'll do first, at least in this video, is we'll talk about what's called the growth function. And this is a complexity measure for infinite hypothesis sets. And the growth function for a hypothesis set H, it takes an argument n, so you put in an integer, positive integer, and then the growth function evaluated at n is this following expression here. So what does it say? It's a rather lengthy expression, so let's try to pass it. So out here on the outside, right, we have a maximum, and it's a maximum over x1 to xn in the input domain, right? So it's basically it's saying take the maximum over all training sets you could get as input, right? Take the maximum over all sets of n points you could receive as input to a learning algorithm. Okay, and then what does it have here on the right, right? So there's a set inside and the size of this set. So what is this set? So let's try to have a look at it here, right? So you have the n points x1 to xn, and then we're looking at the set containing for every hypothesis h in the hypothesis set. So this is an infinite hypothesis set. We're saying look at all the different hypotheses and generate the vector whose ith entry is the label assigned to xi by this hypothesis. Okay, so you get this vector, and then basically we collect all these vectors in a set. You know, so if two of these vectors are the same, they only count once in the size of the set. So it's not a multiset, it's just a set. So basically, this whole expression here is looking at the number of different labelings that the hypothesis set can assign to the points x1 to xn. Okay, so the growth function of a hypothesis h for given input value n is the maximum over all sets of n training points of the number of different hypotheses or different labelings, that you can generate on these endpoints using hypotheses from H. So I think we need to see a couple of examples to grasp this definition. Okay, and maybe just a terminology thing, any such vector here, right, which assigns a label to each of the endpoints from a hypothesis in H is called a dichotomy. Okay, so it's the number of distinct dichotomies we can generate on any set of on the kind of the worst set of endpoints. Okay, so let's have an example. So let's say the input domain is real numbers, so it's the 1D data set, and the hypothesis set is the set of all positive rays. So I'll show you in just a second what is a positive ray. And let's say that n, and we're trying to figure out what is the growth function for 4 points. So, okay, so here's an input, right, of 4 points. So there are 4 examples here. And this is a positive ray. So a positive ray is a ray that starts in some position on the line here, and then it goes to infinity upwards. So it goes in the positive direction upwards to infinity. And then if they say that, you know, for any such positive ray, this gives a labeling of the points, right? So you can say everything after this, the start point of this line is labeled -1, and everything before is labeled +1. So this, in some sense, is similar to the hyperplanes, right? Where we're saying that everything on one side of the hyperplane is one class and everything on the other side is another class. This is very similar in 1D, at least, right? Then the hyperplane is basically everything from some point and onwards is one class, and everything before it is another class. So this is kind of similar to the 1D case of hyperplanes, except maybe in the hyperplane case, we could also have negative rays, that start at a point and go to -infinity. So this is an even simpler set of hypotheses. So this hypothesis said, right, it can have multiple different hypotheses, different rays that give the same labeling, right? So if I start the ray here, I start it here, it gives the same labeling of these 4 points. Right, so this is again similar to if you think about hyperplanes, right? There can be many hyperplanes that actually assign the same labeling to a set of points. If you just move the hyperplane just a little bit, right, you get the same labeling. Okay, so you could also, you know, have a positive ray that spans all the 4 points, and this would generate this labeling of the 4 points. So if you look at it and look at what are the different ways we can assign labels to these 4 points using a positive ray, then you'll see that there's really only these 5 different labelings, right? You can either make all of them red, like in the last case, right? Or you can maybe exclude the first point, make the rest of them red, exclude the first 2 points, make the rest of them red, exclude the first 3 points, make the rest of them red, and maybe exclude all of the points from the ray, make all of them blue here. And so there are these 5 different ways that we can generate 5 different labelings of these 4 points. So there are really, and each of these labelings here, each of these 5 rows is what we call a dichotomy. So there are 5 dichotomies we can generate here. Right, so which means, right, so the growth function up here, again, it's the maximum over all sets of 4 points, or endpoints in general. And here we gave an example of 4 points where the growth function was at least 5, or was exactly 5. Which means that this maximum here is going to be at least 5, right? Because the maximum for all point sets is at least as large as the growth function on this concrete point set. Okay. So maybe just to make it clear, right? You could also have a point set of 4 points where there are 2 points that are sitting on top of each other. Which means that, okay, you can still have this positive ray here, making both of these blue and those 2 red. This one will do the same. And finally, if you include all of them, you know, they're all going to be red. So this is another valid point set. And if you look at it, for this point set, we can only generate 4 different dichotomies, right? Because you either have to include both of the first 2 points or only or none of them, right? You cannot include just one of them. So here we can only generate 4 dichotomies for this point set. But the important point is that the growth function here is taking the maximum over all sets of endpoints. So it doesn't really matter that we have this degenerate point set with points on top of each other, because we can always, the maximum is going to take something that's better. It could still take the one that we saw before with 4 distinct points. So because we're taking the maximum, the growth function is at least 5, even though there are examples of inputs here or point sets that have smaller growth function, where the actual number of dichotomies we can generate is smaller. Okay. Good, so the growth function of positive rays evaluated at the integer 4 is at least 5. Let's also argue that it's at most 5. that no matter what, so what we have to prove here now is to say that, well, no matter what point set, right, because we have a maximum, no matter what point set you give me of 4 points, there's at most 5 distinct dichotomies I can generate on this point set. And the argument is basically saying, okay, so basically now we have to say that no matter what 4 points, right? So if you give me 4 points, x1, x2, x3, and x4, I have to argue that I cannot generate more than 5 dichotomies. Okay, so how would that argument go? Basically, the argument would say, well, take those 4 points. We don't know what they are, right? They're just given to us as input because we have to argue that no matter what 4 points you choose, the growth function is at most 5. So what you could say as an argument for this is to say, okay, you give me 4 points. Now order those 4 points arbitrarily on the line. Right? You can order them on the line in increasing value and break ties arbitrarily. And then it's not very hard to convince oneself that any possible labeling I can create on those 4 points is going to be one of those over here, right? Where the columns here correspond to those 4 points in the sorted order on the line, right? So maybe x4 has the smallest coefficient, so maybe x4 is this one, maybe x2 is the second one, x1 is the third one, and x3 is the fourth one, right? Depending on their ordering. But no matter what 4 points you give me, I can always order them on the line, and then any labeling I can generate will be one of those 5 over here, right? So, which means that the growth function cannot be larger than 5, in particular, it therefore equals 5. Okay. So what about general n, right? So this was just 4 points. What can we say if we have more points? And in general, right, we can give the same argument, right? That if I have n points, x1 to xn, and I want to show that I cannot generate that many dichotomies. The way I could do it is again say, okay, to take these n points and order them on the line. Now, any labeling that I can generate, any dichotomy I can generate, well, you can basically describe it by saying, what is the first point in this ordering that is included in the ray, in the positive part of the ray, right? Because I know that every point from there and onwards are going to be red, and every point before it is going to be blue. Which means that basically any one of those different dichotomies I can generate will be basically completely specified by saying what is the first point in this sorted order that is included in inside the ray. Which means that all I can do is I can generate at most 1 plus n different dichotomies, right? Either the empty set where my ray starts after all the points, or I can generate one that starts between any 2 of the other points, right? Maybe if there's overlaps here, I can only like if several of the points are the same, then I can generate even fewer dichotomies. So this is clearly, if I just want an upper bound, it's at most 1 plus n. Okay. So maybe just to make it clearer, also again, just to take another example. Let's say instead of having positive rays, let's do intervals, which means that, so I have again, the input domain is one-dimensional, right? We just have points on the line. Now my set of hypotheses are all intervals, so which means that I have a starting point and an ending point. So it goes only here from the beginning of the arrow to the end of the arrow. And everything inside I color red, and everything outside is blue, right? So let's say that these are the different ways, these are the different hypotheses that I can choose from. Right. So again, there can be multiple hypotheses that generate the same labeling, the same dichotomy of the 4 points. Right. And you could also have you can also classify these 2 as red and the remaining 4 as blue, and so on, right? So for this point set, right, the different dichotomies I can generate are all these up here, right? Basically, you have the starting point here. You can see that do I include all these up here, include the first point, and then I have a different dichotomy depending on how many of the remaining 4 points I include. Here are the ones where I start at the second point, start at the third point, start at the fourth point, and so on. Right. So the growth function here for 4 points is at least 11, right? Because I can generate 11 different dichotomies on these 4 points, this example here, and we're taking the maximum in the definition of the growth function. Again, right, you can do the same argument that if I have overlapping points, then, I can still generate the same labelings, but over here, I include both. And as you can see now, if I look at all the different dichotomies I can generate, I'll be missing some of them, right? Because I either have to include both of the first 2 points or none of them. So I can only generate these dichotomies over here, But the important point is that the definition of the growth function says we should take the maximum over all sets of 4 points, or n points in general. So it's really at least 11. So these were the 11 dichotomies that we saw before in an example of 4 points. And now we can also show that indeed it is actually at most 11, because I can kind of do the same arguments before, because if I have any 4 points, x1 to x4, I can order them on the line, break ties arbitrarily, and then if they were ordered on the line, then any labeling a dichotomy I can generate will be one of those that I see over here, right? It has to be one of these 11 dichotomies that I have on the right. Right? There's no way I can generate other labelings, right? There's no way to generate a labeling that includes, or an interval that includes the first point and the last point, but none of the ones in between, right? That's, if they're ordered on the line, that's just not possible for an interval. Okay, so it's actually equal to 11, the growth function here. And you can then again ask, what if I have n points? Let's just try to repeat the argument, right? So if I have n points, x1 to xn, then I could order them on the line, break ties arbitrarily, and then any classification or labeling that I can generate, if I use an interval, right, then I can basically describe the labeling by just saying what is the first included point, what is the last included point of the interval, because everything in between those two is going to be red and everything else is going to be blue. And I know that's how the dichotomy would look like. So I can do that, or I can generate the empty set. So if you count how many ways are there to choosing an xi that's less than or equal to an xj, or the empty set, you get an expression like this one: 1 plus n squared half plus n half. So you have a general expression here for the growth function. And this one you can see here grows as n squared, whereas the previous one grew as n. Okay. Let's do one last example, this time for 2-dimensional points. So let's say the input domain is R2. And let's say that my hypothesis set is any convex set, so I can choose a convex set, and anything inside it is the red class and everything outside is the blue class. Now, can we argue about the growth function here? In particular, can we give a good upper bound on what is the growth function? Right? So in particular, we notice here that we have to say what is the maximum over all sets of endpoints. So here's a set of endpoints. I take endpoints and place them on a circle, which means that they're in what we call convex position. And now what I can see here is that, let us choose any set of the vertices here, any points on the circle. Then I can draw a convex set that includes just those points and none of the other ones, right? So I can also choose these 3. I can generate a convex set containing just those 3. I can create a convex set containing just those 5 points and so on. I can do this for any subset of the points. I can generate a convex set that contains exactly those points and none of the rest, which means that I can actually generate 2 to the n distinct dichotomies on n points. I can generate all of them, right? Of course, if I have n points, there's at most 2 to the n different labelings, right? You can choose either red or blue for any given one of them. And here you can see that, well, there is a way to choose n input points where using convex sets, I can generate all 2 to the n different dichotomies. So the growth function here for convex sets is 2 to the n. Okay. So you can see here, this actually does distinguish give some different complexity measures for different types of hypotheses. You have the positive rays, which are also intuitively the simplest hypothesis set. The growth function was 1 plus n. For intervals, so you can choose a range, and everything in this range is inside is labeled red, and everything outside is labeled blue. There, the growth function was something close to n squared. And if my hypothesis set is basically all convex sets in 2D, if my input domain is 2D, then I have an exponential number of hypotheses. I can generate 2 to the n different hypotheses. Okay. So what we're going to do now is we can actually show that we can actually use the growth function to give generalization bounds, right? To give statements similar to this one that we had before, relating the in-sample error and the out-of-sample error of the hypothesis learned by a learning algorithm to the number of training examples and the complexity of the hypothesis set. So of course, right, a natural question to ask, right, is, well, okay, for the finite set, if we actually had m different hypotheses, then we get a bound where this m occurs here multiplicatively. I guess we could ask ourselves, could we just plug in the growth function of n in place of this capital M, right? And maybe in some sense it could make sense, right? You're saying, okay, my training example set has only n points. So in some sense, my hypothesis set can actually only generate this many distinct hypotheses, right? The growth function of n. So one could maybe believe that that this could be a true statement. Of course, the issue is, right, the one thing we have to be careful with is that the set of hypotheses that you can generate on n points, it's going to depend on the training data set, right? You get n examples, and then the different hypotheses you can actually generate on this set depends on the data set, the training data set. So it's not clear that this union bound with Hoeffding's inequality that we did to prove the first one, I would go through here, right? At least if this was true, right, we can plug in a value here and we would actually get a bound that's meaningful, right? We'll get a finite expression here on the right-hand side that may become meaningful. And it actually turns out that this is almost true. We can almost just substitute this capital M with the growth function instead. And here's a bound that one can actually prove, right? If you replace the constant here by 8, instead of applying the growth function to n, you apply it to 2n. And instead of having a 2 in the exponent, you have a 1/8. Then this is actually true. You can actually plug in the growth function. Okay, we're not going to give the proof here. It is significantly more involved than just doing a union bound over a fixed set of hypotheses, right? You need a couple of really neat ideas to carry this proof to the end. So, but that is so for these videos, we're just going to use this as a fact that you can replace the generalization bound for the finite hypothesis set with one involving the growth function when we have infinite hypothesis sets. Okay. So, if we apply this to the different examples that we saw, for instance, the positive rays, right, we have to double the n. And so if we plug in what we computed as the growth function before, the growth function was 1 plus n. We have to apply it at 2n, so we actually get a 1 plus 2n here in front. And for the intervals, right, if we plug in the growth function we computed before, evaluated at 2n, you get this expression here. And finally here, if you plug in the growth function that we had for the convex sets, this exponential in the 2 to the n growth function, we plug in 2n, then we get 2 to the 2n. And the factor 8 here, we can also move into the exponent. And so now we actually get generalization bounds telling us something about how close we can expect the in-sample error and out-of-sample error to be if our hypothesis set is either positive rays, intervals, or convex sets. And this is really interesting because these are actually infinite hypothesis sets. And in particular, if you look at the first two examples here, right, you can see that in the exponent, right, we have an n up here in the exponent. So the latter term goes down exponentially fast with the number of training examples, whereas the first term here only grows polynomially with n, right? So this is going to be non-trivial. It's going to give us something non-trivial already for small sets of data, training examples. And so this is really, it's really useful. If you look at the last one here, right, I guess we have two exponential expressions. One of them goes down exponentially fast in n. One of them goes up exponentially fast in n. If you actually plug in the numbers, you realize that this guarantee down here is more than 1 for all n greater than 1 and all epsilon less than or equal to 1. Which means that it's really a meaningless bound for convex sets, which also in some sense makes sense, right? If you think about it, I give you a training data set. If you think about this example again, where all the possible data points are sitting on a circle, your training example only contains a subset of them, which means you only know the labeling on the subset, which means that if you have to pick a convex set for everything you didn't see, you basically have to guess whether its label is blue or red, right? Because there's basically a convex set that can do any of these different dichotomies. So in some sense, it makes sense that you cannot really hope to argue that if I use convex sets as my hypothesis set, then I can guarantee you that the in-sample error and out-of-sample error are close, right? Because I can get a 0 in-sample error using a convex set. If you look at the circle, I can get 0 in-sample error by just choosing a convex set that has exactly this labeling on the points I receive. And for all remaining points outside that I didn't see in my training data set, there's a convex set for every possible labeling, so I have to choose one of them, and this might just as well be completely wrong. Okay, so that's just to say that this is to be expected. If the growth function is 2 to the n, then you cannot really hope that you can learn it. Okay. So, so now we saw the growth function, and it actually gives us meaningful bounds. You can plug it in, you can compute an upper bound on the growth function, and or at least, if you know an exact formula for the growth function, you can plug it in up here, and you get a guarantee on the closeness of the in-sample error and out-of-sample error. And maybe one observation here is that if you want to use this formula, right, we basically just want to show that this right-hand side is less than or equal to something. Right? We just need an upper bound on the growth function, which of course were the hard ones to do, right? These are the ones, if you remember, right, for the intervals and the positive rays, these were the ones where we had to say that, no matter what data set you give me, I can order them on the line, and then any possible dichotomy is a subset of this small set of dichotomies. So the hard part was really proving upper bounds, but you only really need that. You just need an upper bound. You can allow yourself a little slack. You get a looser bound up here if you just upper bound it by something bigger, but this may help. And this is what we'll try to do. In the next video, we'll see a simple technique for giving upper bounds on the growth function that you can then plug in. And this gives you sometimes a simpler task of proving generalization bounds. Okay, so let's end there and continue in the next video by seeing a method for upper bounding the growth function.